Welcome back. In this episode, we construct the Alloy Blast Smelter, an advanced machine that fuses the capabilities of a mixer and an electric blast furnace. It's the ultimate tool for crafting high-tech alloys. This is Star Technology. Let's get into it. So since the last episode, I spent a bit of time just improving a few things and making use of that new energy hatch, performance improvements and just little things like that. One of the big changes I've done is in here in the clean room. I've moved all the circuit assemblers that were over here and put them here and upgraded them to circuit assembler 3s. I went to craft some of those energy hatches. I wanted to create 32 or 64. It was taking a really long time. So basically, I wanted to improve that. Just created a whole bunch of these. Laser engraver with the glass lens that's brown produces the MPIC wafer, which is useful in making a whole bunch of stuff, including the HPIC wafer. I needed a lot of them. And as you can see, what I've actually done is create a large chemical reactor in here instead. So this is running off the new power, which means that it is actually running at ludicrous voltage, which is pretty cool. I also created the crafting terminal here. I don't know why I haven't done this sooner, because whenever I'm working in here, I'm having to constantly run out the door, run back in. I think what I'll do is I'll create a whole bunch of these around the factory in more useful spots instead of having to come back to the central location all the time. I've upgraded some of the key pieces of infrastructure with the new hatches. The first one being this shellite. They're using the IV energy hatches now. So that's running twice as fast. That's useful because obviously we need a lot of shellite. Let me silence these machines. I like the sounds of the machinery working, but sometimes it's just overwhelming. And the main electric blast furnace. So I upgraded that to use the new IV energy hatches as well. End result of that is we're using a lot more power than we used to, but the power setup here is very expandable, so that's what I've done. As you can see, the output is now over 500, getting close to, up to 600,000 RF per tick. So what I did was I did the planned upgrade I was going to do for these compression dynamos. So each of these now have an EV upgrade kit, one auxiliary reaction chamber kit, and two multi-cycle injector kits of the highest tier that I can make. So the end result of that is it's at 300% efficiency. So that means that the fuel lasts 3 times longer, and it's producing 153,000 RF per tick. And so I've got 10 of those. So my power capacity now is 1.5 million. Something interesting did happen. We built this indium creation thing here. It ran for a little while and then just stopped. It ran out of aluminium dust. So I was like, oh, okay, that's weird. Are we not recycling that properly? I've discovered something I missed when we first created it. When you have the indium concentrate and you react that with 16 aluminium dust, you get 16 aluminium sulfide out. When you electrolyze the aluminium sulfide, 14 goes in, but only 2 aluminium dust goes out. So there's a net loss of 12 aluminium for one cycle. The whole process consumes just over 12 aluminium dust to make one single piece of indium. I didn't factor that in. So I haven't had to create aluminium dust for a long time because quite a few episodes ago now, I created that clay electrolysis, and that created so much spare aluminium that I've been running through that stockpile for all that time and never had to do anything about it. I wasn't even processing bauxite, which is one of the main aluminium bearing ores, because I had thousands of it, but I've completely run dry. I've had to change my ore processing to include bauxite in it. So yeah, I didn't expect that. So that's something to be aware of when you get to that stage with the indium. You are going to need a load of aluminium. I've been looking at a few different things in the quest book as to what we should tackle next. My gut feel was, okay, let's sort out this stuff here to get these epoxy printed circuit boards, like I said. I was thinking about this Alloy Blast Smelter a bit, and I was trying to figure out how hard it would be to make that, and maybe it's something that we could set up, and then it could be cooking up all these ingots for us in the background so we can do these upgrades. And I thought, well, I actually don't know much about this Alloy Blast Smelter, so I thought I'd check out how hard it is as a block to make. And this is it here. It's not too bad. The most unusual thing here is the tantalum carbide plates, but we have tantalum and carbon, and so we can make that. The heat vents involve something called molybdenum disilicide, which we haven't seen before, but I think that's probably achievable. High temperature smelting casings. Similar things to what we've got. I mean, it's probably at the edge of our tech, but it's all doable. The Alloy Blast Smelter is really a mixer and an electric blast furnace in one. The typical process for making, say, tungsten steel involves mixing tungsten and steel in a mixer, which produces 2 tungsten steel dust. Then we run the tungsten steel dust through the electric blast furnace, which produces a hot tungsten steel ingot, Then we put that hot ingot into a vacuum freezer and that produces the tungsten steel. With the Alloy Blast Smelter, it actually cuts down on a step. We can put the two dusts directly into the Alloy Blast Smelter and we get molten tungsten steel. And then using a vacuum freezer with an ingot mold, we can create tungsten steel ingots. Okay, well I think we need to build an Alloy Blast Smelter. What do you think? This is what it looks like. It's a cool looking multi-block. It's pretty big. It's got a footprint that's pretty much 5x5. It's got 2 rows of coils, which can be upgraded. So it uses 24 instead of the blast furnace, which only has, 16? Well, I will try and figure out where I'm going to put it. Maybe somewhere in this area, like maybe here. So I spent a bit of time just going through encoding all the recipes that we'd need for the high temperature smelting casings and the heat vents, as well as the Alloy Blast Smelter. It was quite fiddly. There was a lot of things we needed to create, new ingots like the tantalum carbide and all that. So I thought I'd spare you all the tedium of that. Nothing too scary in any of that. The only thing that we did have to do, one of the 2 carbides required an upgrade to the mixer. It requires an IV mixer, so ours was only EV, so I had to upgrade that, which took a little bit of time because the wiring underneath down here is a bit of a mess, as you can see, because of the platinum line underneath. Being able to just place these flux points anywhere we need to get power is brilliant. Because previously I'd have to run power cables and try and make sure that they don't intersect, and yeah, anyway. Huh. So my lights have gone out. All right. I guess I need to fix that. Everything that comes out of the Alloy Blast Smelter is a molten substance, like molten tantalum carbide, molten molybdenum disilicide. So that's how you can distinguish them from the liquid versions of the metals, because obviously the liquid ones don't need to be run through the vacuum freezer, but the molten ones do, because they're equivalent of a hot ingot. So with that in mind, I thought, well, everything that comes out of the Alloy Blast Smelter, we'll want to convert into an ingot immediately. So I'm going to build a vacuum freezer next to it. The molten liquid will just flow straight into there and then be solidified. And all we've got to do is make sure that the vacuum freezer is quicker than the Alloy Blast Smelter and nothing should build up. Let's start with the energy hatches. Then we're going to need some of these high temperature casings. Then the block itself, and then a row of coils. Then some of these heat vents. Another row of coils. And then just finish off the block. Muffler hatch up there, and a maintenance hatch here, which I forgot. All right, that block is complete. Cool. Okay. Now, obviously, we need some inputs and outputs, but we'll do them after we've done the vacuum freezer, I think. Put in the hatches. Got the multi-block. Put a maintenance hatch. And the muffler, and then we just fill everything in. Done. Now we're going to need inputs and outputs. We'll start with the vacuum freezer, because the vacuum freezer is going to need to have this casting mold for ingots in it. So that means at least an input bus, but also it's going to have the liquid that is coming in. So we'll have an input hatch. I'll put the input hatch here, and then I'll run a pipe from there to there. And I need an input bus. So I might just put that on the side here. So the only purpose for that is to actually contain the casting mold. Then what we're going to need on this side is the output. So we're going to need an output hatch. And we're also going to need an ingredient buffer and all that. So let's look at something fairly typical. So we're going to have a bunch of dusts and some kind of gas. So what we could probably do is just do what we've done with the blast furnace, maybe towards the back here. One there, and maybe this one as well. Put in an input hatch, input bus, ingredient buffer on that. Put the item pipe in like that. Do the extract, so that should go in there. And now we need to hook this up. So in theory, that should be it. The components required to build one of these Alloy Blast Smelters involve these 4. So we need tantalum carbide, molybdenum disilicide, titanium carbide, and tungsten carbide. So setting up those 4 in this Alloy Blast Smelter would allow us, in theory, to build them quicker. So that might be a cool way to go. So we're going to need program circuit 12. Well, I'm going to go encode some recipes and then stick a buffer on here and then just cable it up, and I'll come back. So I've gone through and encoded all these patterns. What's interesting about these is I've had to encode them with the ingot in mind, not the molten metal. So what I wanted to do first was actually do a test to see how long it takes to process one of these with the current setup and see if there actually is an improvement with the new system. So if I try and craft 2 of these tantalum carbide ingots and then start a stopwatch, how long does it take? So that took about 24 seconds. So if we go in here and remove the tantalum carbide from there, put the new one into here, that'll be a good test. And then request 2 of those. Oh, look at that. Lit up. Oh, that makes a cool sound. I forgot to set a timer. Oh, that's amazing. Okay. I have not had that happen yet. It's clear why that happened. It's a polytetrafluoroethylene fluid pipe, and I just put molten metal through it. So that's never going to work. Oh, that's cool. I didn't know that mechanic existed. What have we got that's actually rated for that kind of temperature? Probably stainless steel would be better, wouldn't it? Temperature limit 2428 Kelvin. This one here might work. Let's try this again. Cool. Cancel that craft because that is not going to be returned. All right, go. Yeah, it's not ideal. Okay, so we need something better than that. Well, I mean, set fire to the vacuum freezer, which is not a good thing. We could fix it by kind of cheating and rebuilding this so that it was up here with the 2 ports facing each other. And it would be hovering in the air, and it would work, and it would look kind of ugly. I don't want to do that. I want to solve this problem. It feels like I would be cheating if I was doing that. All right, so we need something better than that. So what have we got? Niobium titanium looks pretty high. Tungsten carbide. Geranium. Okay, that would be ideal, but we can't make that yet. Oh, okay, just tungsten. Tungsten is famous for having a very high melting point. This should be rated for 4600 Kelvin. Does it say what temperature this is going to be at? Yeah, it does. On that tooltip, it says it's 4120 Kelvin, 2300, 3400. So I've got to be careful with some of them. I'm guessing that later on, they're going to be much higher. So I will have to replace this tungsten fluid pipe with better ones. Cool. All right. So this time, I think it will work. That's looking better. And then that's what... Oh, geez. Okay, that was quick. We've solved the melting problem. And we've got our 2 tungsten carbide things. All right, so now we need to time it. So let's kick this off. See how long it takes to come back. 22 seconds. I can't remember what I said the last one was, but it'll be on this recording. So I will look back at it and figure that out. So I looked at the footage and it looks like the old system took 24 seconds. So the new system is 2 seconds faster, which isn't a lot. But when you look at the actual test, the 2 tests went exactly the same because we actually had 2 electric blast furnaces working in parallel to achieve that. Each cycle of electric blast furnace only produces 1 ingot, whereas the Alloy Blast Smelter produces 2. So in theory, that 24 seconds should actually be much more. It should be more like 40 seconds. The fact that the new one is 22 seconds is pretty amazing. But what we can probably do to even push it even further is to actually build a second Alloy Blast Smelter and just wall share it. So maybe that's what I'll do. All right, so I've created the second one and got the wall sharing going. Basically, we've got double the speed now. So what was previously 22 seconds is now technically 11. So I guess we should tick off the Alloy Blast Smelter because we've definitely done that. And now we can actually start making some of these. What are we going to actually aim for? In theory, we should do these in order because that way we'll unlock them in order. We probably should start encoding some of these and just making them ink alloy. So how do we make that? There's 2 recipes. Oh, of course there's 2 recipes because one has helium. Oh, that's slow. Vanadium, steel, manganese, aluminium, yttrium. Program circuit 14. We don't have that. I've been lucky so far because all of the ones I wanted to make have been on the same program circuit, which is 12. That's easy to set up here and also easy for it to share it. But I've used up all those 3 top faces, which means I'm running out of blocks that are shared. Like there's really just this one down here and then the other one on the other side and then the one underneath, which is going to be hard to get to. So what I might do then is go away and figure out a solution to this program circuit problem and then come back. Recently, I ran a poll in the community section of the channel just to see what people were interested in seeing. One of the options I gave was base building, and that's something I haven't really shown much of as I've been building this all out. Fair few people that actually said base building was something they wanted to see. I haven't decided yet how I'm going to make that happen, but I might just share what I'm planning to do. My process is a little bit chaotic, so I was just cruising around. I decided to come over here and do some more bone meal. And as I'm approaching this section here, I thought, hang on, that almost like a sewer. So I thought it'd be very cool to have this be a tunnel that goes in, probably made of this stone. Put lots of like mossy blocks around it so that it looks damp and dank, I guess. And then have water actually coming out of it, like flowing down this way. So I'll extend these dirt platforms out a little bit so that it, I guess, like flows a further distance. And then figure out what to do with it and maybe make it go into some kind of effluent lake or something. Maybe this could be the discharge for the industrial part of the plant. Or maybe it's just a sewer vent, I don't know. But yeah, that's where my head's at. I'll probably do that at some point. So I've done some brainstorming and I'm pretty confident I've got a solution to this. So let's get into it. Probably the easiest way to explain is probably to look at the actual recipes and something that I've just discovered. So let's take, for example, this recipe here, which is for molten rhodium plated palladium. We haven't used that yet, so I'm sure that's going to be something we're going to have to use soon. But the recipe requires 2 inputs, and it's on program circuit 2. This one here, which is the same recipe but quicker, that uses a gas as well, is on program circuit 12. If we go to a different one, like this liquid vanadium steel, 3 inputs, 1 gas, program circuit 13. It seems like the program circuit that's used is the number of inputs, plus if you've got a gas, it adds 10 to it. So if we go to any random one here, this is 2, that's 12. 12, this is 4, because there's 4 inputs. So that seems pretty reliable. So yeah, that's pretty cool. I didn't realize that. So the program circuit is equal to the number of inputs. The interface for a mixer can only take 6 dusts. The whole thing about the Alloy Blast Smelter is that it does the mixing and the blasting in the same step. So you provide the raw dusts and it provides you the alloy rather than having to mix it first. Therefore, there shouldn't be any recipes that have more than 6 dusts. So what that means is there's program circuit 1, 2, 3, 4, 5, 6. But we want to do it with the gas to make it faster. So that means 11, 12, 13, 14, 15, 16. So with that in mind, I have created all the different program circuits from 11 through to 16. Both of these are kind of joined together and are on 12. For the moment, I'll leave them there, but eventually I'll dismantle them and build one here and then use the other one for a different one. But what I want to do right now is build one of these blast smelters that works for program circuit 13. They will be molten RTM alloy, liquid black steel, liquid vanadium steel, liquid signalum, liquid lumium, molten HSSS, bismuth bronze, canthol, enderium, and black bronze. So all of them are on program circuit 13. So that's the plan. What I wanted to do though is try out something new. So there's this thing called a terminal, which I've recently learned about, which is a very cool little gadget. So I am going to give it a try. We'll see how it works out. So what I've got is I've got the Alloy Blast Smelter. I've got all the ingredients to make an Alloy Blast Smelter in my inventory, including all the hatches and the muffler hatch that I need. So what I'll do is I will build it here. So let's place that block. The terminal will let you automatically build this entire multi-block in one step. So if I shift right click on this, check that out. That instantly built the entire multi-block. And in fact, because I had all the hatches, it's ready to go. Like it placed every single block, including the muffler hatch, including the maintenance hatch at the back and the IV energy hatch. Now, these don't match up to where I want them to be, so I'm going to have to move them. But this is a huge time saver. The funny thing is, I don't know how I feel about that because I actually enjoy building the multi-blocks. So I'm not sure how I'm going to go, if I'm going to use this a lot or not. I'd be interested to know what you guys think as well. There's a little bit of stylization I do in the editing for when I'm building a multi-block. If I'm just building it with the terminal, then that would all go away. So here's the very complicated recipe for the terminal. You probably won't build this until very late in the game because it's made of things like books, glass planes, and raw iron screws. So yeah, I'm joking. You can build it from basically ULV. A little bit annoyed I didn't find this earlier, to be honest. Terminal seems pretty useful. Probably for building multi-blocks that you've never tried and it might be kind of tricky to get right, the placement of some things. I had a few builds early on where I tried it just didn't work. I had to fiddle around with lots of different combinations and I just couldn't quite figure it out. So this could create the baseline very quickly and then you can just tweak it to add the hatches where you want. Like something that will be coming up in the future, something called a rotary hearth furnace. We won't be building this until a long time. This is like, ZPM and Naquadah and all that kind of stuff. But it's a replacement for the electric blast furnace. But check out this guy. How good does that look as a block? That would be, it would take a long time to build by hand, but I think it would be kind of fun. Like I'd want to actually try and build that by hand rather than just click a button and it does it for you. Like if you add up these numbers, it's like 600 or 700 blocks that you're going to have to place. It depends on how you want to play the game, really. If you want to just get to the end result of having this thing, you can click the button. Otherwise, just build it by hand. And you know me, I'll probably build more than one of these. Cool. Let's get this properly configured because I don't want that to be there. And I don't want that to be there. So let's place that there. And let's put the two IV hatches in there. Move them into place. There we go. Auto maintenance hatch. I like putting them at the front. All right, so let's hook this up. So this is all going to be program circuit 13. An input bus, the input hatch, and then an output hatch. Ingredient buffer on the input hatch, and then an item pipe like that. Tell it to extract automatically. We need a pattern provider on here, a storage bus on here. Because what I'll do is, even though I had that fun with this pipe here, what I will actually do is rather than using a pipe to hook it over, I will use the ME system. So I'll set up an interface on here to request it. We need to have another hatch. So we'll have a LV input hatch on that. This is a good point to show something else I discovered. There's interfaces and there's extended interfaces, and that basically just doubles what you have. But there's also something called an interface upgrade. So you can actually use this to upgrade an existing interface. So I'll place this interface here. As you can see, it's got those 9 slots, but using the upgrade, now it has 18. Yeah, let's set this up. So do that. Do that. Cool. Okay, that should be all of those. So now I need to encode those patterns. So let's go do that. So encoding these patterns, it's actually pretty crucial that you check every single one of them. The very first one I've gone to encode, I can already spot an error. This tungsten dust that actually needs to be 2, not 1, as the recipe there shows. Also, obviously, we're removing the program circuit from each of them. Yeah, you have to be vigilant because you've got to check that these are correct. And last one, black bronze. Okay, so out of those 10, only one of them was working correctly. That's good to know. Okie dokie. All right, so let's upgrade this. And now put in all these patterns. In no particular order. Ah, I've just realized I've done them wrong. I needed to have the output be the ingot. Okay, let's go back and fix that up. Oh, that's annoying. All right, I'll spare you guys that bit. Okay, I've fixed up those issues and just placing these in here. So that should be all of them all set up. Now, the next thing I need to do is actually remove those from the blast furnace because we have blast furnace recipes, obviously, for the original ones. Okay, so let's give this a go. Let's try requesting something. So let's try, well, Indirium is one of them, isn't it? Let's try 32 Indirium. Ah, okay. I forgot one small but crucial detail. You got to set the program circuit. So this was all for program circuit 13, wasn't it? So let's do that. And now it's working. So that's good. So what I'll have to do is just over the course of, time is actually just test each of the recipes, make sure nothing has gone wrong. But there you go. So I think that wraps it up for this episode. We got through quite a lot, but obviously that misadventure with the molten metal kind of delayed us a little bit, so I didn't get to the mystical agriculture stuff that I was hoping to. But that's okay, we'll cover that in the next episode, I think. So that's going to be pretty exciting. Thanks for watching, and I'll see you in the next episode. Cheers.